Hey, welcome back to the HTH 2021 CTF Solve video series. I'm John, and in this video, we're going to be taking a look at Pwnable Challenge 3, which is called Return to Normal. So let's go ahead and get started. In this particular challenge, we're going to be taking a look at the binary, which we can download from the scoreboard. It tells us that essentially we need to exploit this remote service. So we have Pwn3 loaded into Ghidra. We're going to take a look at this in a minute. Let's go ahead and interact with the service. It also tells us where to connect and how to connect so we can interact with it. If you've seen the other videos on the Pwnable challenges, this will look very similar. So it's going to ask us for a command. We'll type one in. It says invalid command. So we need to go ahead and try to find what we have to do here. So in the challenge, what we're going to do is just kind of follow what's going on here. So we have a variable called user input. It's 100 hex or 256 bytes, and that gets set to 0. Then we're also going to ask the user for a command. We're going to read input into that command, strip off the return or carriage return or new lines, and then we're going to null terminate the last byte in that string, and then run check command. So let's go into check command. Inside of check command, it's going to take backup. And it's going to be looking for backup as the first 6 bytes in that string. So one of the issues that I see here, one of the issues is that this is 32 bytes. And if we go back to where check command is called, it's passed a pointer to a stack buffer that's 256. So we can effectively get 256 bytes into a buffer that gets processed with stir copy into local 28. That's only 32. So that's a problem. This whole stir copy is unnecessary, as we could just check the comparison between the user input 256 and backup. But that's the way the challenge works. So we'll take it. So in this particular case, we just need to have our input start with backup. So if we connect to it and we do backup as our command, it will tell us command accepted, functionality removed, heart TSK. So if we get through this, it's not actually going to return from this function. It's going to exit. But if we can get backup located here or into this, it will return. So if we overwrite that return address on the stack, we can end up pointing somewhere else. So if we take a look here, we look at systems or system calls here. And if we check out the return or cross references to this, we'll see that there's one for debug shell. So we double click on that. This looks perfect. So it takes no parameters. If I can just return to debug shell, it will print out bin bash. Now the location of this is 401256. All right. So let's see if we can end up doing this. What we have to do is end up calculating what that looks like, the space here. I'm going to just kind of change something really fast. So this is the whole cat portion of this is to keep standard in open so we can interact with it. This is the same location where we're connecting. The first part of our buffer is going to be backup. Then we're going to add 26 plus 8 bytes of padding. And then that's going to put us directly at the location where we want to overflow and then return. This address, 401256, is actually taken from a couple of different locations. So let's see how we can find that. First of all, in here, there's 00, and we don't put the null byte in there because that would terminate our payload. But 401256, and we flip that because of Little Indian. All right, what other way can we use to do this? Let's do readelf, readelf-a on ret to normal, and then we're going to grep for, I think it was called debug shell. There we go. Also, the address is right here too. So I'll do gdb ret to normal, and we'll do the last way. I can do disas debug shell. I'm forgetting what it's called. And that will give us the location right here. This output in GDB is called Jeff. I say Gef, but I guess it's supposed to be called Jeff. So that's one of the sort of GDB helper scripts that kind of formats everything pretty nicely. All right, so let's throw this thing and see what happens. And how do we know sort of what these spacing and bytes and all this padding that we have to do? One, we can do it just by testing this locally. We can load up GDB, we can start debugging it and seeing how the stuff works. Or we can take a look at the main function and try to understand how far we need to get in order to do this. So we know whatever we get passed in here is going to go into check command. We need 32 bytes to overwrite this guy and then go down into the return. So we have 26. If we add 4 of this, that's going to be 30 plus another 2. And then we need some to get past the base pointer. And then we'll get here. So it's really just a matter of playing with this and seeing where your bytes come into it. You can add a cyclic pattern from something like Metasploit, or you can just kind of add it up and see it yourself. But as you start with things like capital A's and capital B's, you'll see hex 41 and hex 42 in the output. This ends up being the correct amount of padding we need to get before this overwrites a return value. And then we try to come back to this function. So let's go ahead and give this a shot and see what happens. Okay, so we didn't get anything there. I type in backup and nothing actually happens. If I do this, I get nothing. So what's going on here? Let's go ahead and take this output to try to debug this a little bit. And I'm going to put this into a file. So I'm going to pipe this to a file called payload. All right, do this. And then what I'm going to do is gdb ret to normal. And then when I run it, I'm going to run it with that payload coming into the run. And then we crash here. So the reason is SigSegV. This particular issue is that we are crashing. Why are we crashing in do system? So we call system, the underlying function that gets called is called do system, and we've crashed on this particular thing. This was something that I've never actually seen before, and I went to try to figure out what was going on and found this article by Pondum. And he actually brings up, or they actually bring up, a really interesting point, which is the same exact instruction that I'm crashing at and have an issue with right here. So I started reading into this, and he gives a reference to this site, which doesn't give it's a very concise answer. But the problem is that the stack is not actually aligned by 16 bytes. So the way that we end up manipulating the application in overflow, there's not a pop to then keep the stack aligned the correct way. So when we enter that particular location, which requires 16 byte alignment, it's actually not. So what we have to do is prevent a push or a pop from getting us out of line prior to calling that. So let's see if there's a way that we can do it. If we go here and I'm pointing it directly at the start of this particular function, which this is check command, it needs to be debug shell. So this is the location where I'm sending it to right now. If we look down, there's a push RBP. So it turns out that we're actually 16 byte aligned as we come into here, but then we push RBP, which then moves us off by 8 bytes. And then we're kind of done at that point, right? So if we can prevent this push RBP from occurring, we can actually remain 16 byte aligned and hopefully get past this bug. To do that, we need to actually return to 5B instead of 5.6. So let's give this a shot and see what happens. I'm going to clear this. Again, I'll put into payload 5B, right? And then we will do GDB. I'll run this with payload. It'll run. Everything worked okay. So we did get a seg fault, but we returned from where we wanted to go. We got debug shell success. This is exactly what I expect to see. So we do crash the application at the end. Totally fine, not a big deal. At this point, we should be able to just keep standard in open and interact with it. So let's go ahead and do that. All right. Let's go back to our initial command where we have this. We will change this to 5B. I will run this and it looks strange, right? I can type something like backup, nothing happens. But if I do a command, I'll then start getting output back. So now what we've done is we've locked that standard in that is sitting there waiting for this cat and this to actually finish. And we can interact with this. So let's do cat flag.txt. Oops. Right, and then here is our stuff. The rest of this is kind of the end of the story of the CTF. But that's pretty much it. So it really takes you connecting with the service, doing a little reverse engineering, understanding the flaw, figuring out that, hey, your payload that should work doesn't work. The way you find that offset is by debugging it locally, and you kind of work through that stuff. So I thought this was interesting to leave in because of that odd issue with the 16 byte alignment in this. Now, anytime I ever get a crash doing a CTF or doing a real world thing, and I see this problem, I'm immediately going to have a red flag that goes stack alignment. That is very strange. But I thought it was really cool. I love seeing this kind of stuff in CTFs as I work through them, kind of learn new things. So that's pretty much it. That's the rest of the CTF challenges. If you have any questions, feel free to reach out on the HTH Discord server. Until next year, thank you.